So for problem number 47, we're supposed to use our calculator to model the data as a quadratic regression equation. So I went ahead and put all of the numbers in my calculator. There's not much work for this to show, so I'm just going to write down what I got. So the equation is going to be, let's see, y equals negative 0.173 t squared plus 8.312t minus 1.386. And instead of y, I should have this be p of t equals, just to match the setup of the table. And for part B, we're supposed to use that model that we just found to determine the time at which the population is the greatest, and we will round to the nearest hour. So for this, we're just going to say that t equals negative b over 2a. This is the equation we'll use to find when our y value, to find our x value or our t value when the population is maximized or the greatest. So to do this, our a is that and our b is this. So this is just negative 8.312 divided by 2 times negative 0.173, and this is approximately 24. So for part C, it asks us what the maximum population is. So what we found in part B is the time at which the population is the greatest. So all we need to do with that is take that time value of 24 and plug that in to our P of t equation. So we'll have that P of 24 equals negative 0.173 times 24 squared plus 8.312 times 24 minus 1.386, and this is equal to 98,500, and that's after we rounded to the nearest hundred. So number 48 is asking us to determine the end behavior of some polynomial functions. So when we're doing that, we only need to pay attention to the first term of the polynomial, as long as the first term of the polynomial has the highest power or degree. And so for part A, let's look at this. So we see that the power is 224 and the constant in front is negative 345. And so the things that are important is that the power is even and the constant in front is negative. So since the power is even, we know that the polynomial function is going to start and end in the same direction. And with an even degree, it's going to start up and end up. However, because the first term is negative, it's going to start down and end down. So in other words, the end behavior of this will be left falling and right falling. Okay, now for part B, again, we're just going to look at the leading term. So the power is 333, which is odd, and the constant is negative 28, which, like I said, is negative. So since it's odd, it's going to start and end in different directions. And usually that's going to be falling and then rising, but since it's negative, that's going to be switched. And so this one's going to be left rising and now we're going to look at part C. The power of the leading term is 289, which is odd, which means that it will usually be left falling and right rising, and it will stay that way because the sign of the constant of the leading term is positive. So this one will be left falling and right rising. Okay, and then part D, the power of the leading term is even, and the sign of the constant of the leading term is positive. So this will be left rising and right rising, because that is the normal pattern of in behavior for even degree polynomial functions. Part E, the power of the leading term is 53, which is odd, and the constant is 2 pi. Even though this is a weird number, it doesn't change anything. It only matters if it's positive or negative. So since it's positive, this one will be left falling and right rising. And then finally, for part F, the power is 88, which is even, and the sign of the leading term's constant is negative, so it's going to be the opposite of what it usually is. So this will be left falling and right falling. Okay, for number 49, part A, well, for all of these, we're finding the zeros and stating their multiplicities. So for part A, we're going to solve this with the grouping method. So what I mean by that is we're going to split this up here, plus negative x minus 7, like that. And so what I'm going to look at is to see what things I can factor out of these. So for the first two terms, I can pull out an x squared. That will leave me with x plus 7. And then of the second two, I can pull out a minus 1, which will leave me with x plus 7. So it's important that after I factor out those terms, that I have the same things left in the parentheses. So then this is equivalent to x squared minus 1 times x plus 7. And so then I'm going to set this equal to 0. Because of the zero product rule, I can say that x squared minus 1 equals 0, or x plus 7 equals 0. If either one of these are true, then my equation will be satisfied. So I'm going to go ahead and solve both of these equations for x. So here I will get x equals positive or negative 1, and here x will equal negative 7. So the zeros here are x equals negative 1, positive 1, and negative 7, and all of these are multiplicity 1.
Okay, so number 52 says sketch a rough graph of the function f of x equals 2, x minus 1 squared, x plus 1 cubed. To aid in sketching the function, find the end behavior, zeros and their multiplicities, and the y-intercept. Well, first, I'm going to list out my zeros. I'm going to do this part. Do this part first. So, put zeros, and I'll do multiplicity, if I can spell, that is. So looking at the function, I'll get a 0 from here, which is 1, and I'll get 1 from here, which is minus 1. So I'll go negative 1, 1. The multiplicity is how many times they repeat, or, in other words, this little power right there and that one right there. So positive 1 has multiplicity 2, and negative 1 has multiplicity 3. Other stuff I need is I might need my y-intercept. So y-intercept is when you plug in 0. So if I do 2, 0 minus 1 squared, 0 plus 1 cubed, you get 2 times minus 1 squared times 1 cubed. Minus 1 squared is 1. 1 cubed is 1. We just get 2. So we'll have the point 0, comma 2. That is our y-intercept. And next, it says it might be good to find the end behavior. Well, or to find my end behavior, I'm going to erase this so we can see this a little better. I need to know whether this is even or odd. So a good way to tell is, let's kind of think about how many x's we have. Well, we have some x's in here, and they're squared, so it's like an x squared. And we have an x here, and it's cubed, so we have an x cubed. So we have an x squared times an x cubed, we get an x to the fifth. There is no negatives or anything on these x's or in front of here. That's going to change that up, so it's going to be odd, and it's going to look something like that, right? So when I'm going to go ahead and graph it, I know a few things. I know I have the point 0, 2, that's my y-intercept. I have the point -1, 0, and 1, comma 0. So I'll go ahead and write 0, 2, 1, 0, minus 1, 0. I know that from my end behavior that to the left is going to be going down, and the right is going to be going up. And now I can use my multiplicities to tell me what happens in between. So how these multiplicities work is if you have an odd multiplicity, when it hits the x-axis right here, it's going to cross over. So -1 has a multiplicity 3, that's odd. So it's going to cross over, it's going to go to the other side of it, right? I'm going to hit 0, comma 2, and I'll go back down to 1, comma 0. But my 0 of 1, I have a multiplicity of 2. If it's even, it's going to bounce off. So it's going to go to 1, it's going to bounce off, and then keep going up to infinity. So this right here is my rough sketch of the graph. Continuing on for number 53, we'd use long division to divide the following polynomials. Give our answer as a quotient plus the remainder divided by the divisor. So I'm going to move it over here. We have 6x cubed minus 5x squared minus 3x plus 4 divided by 3x plus 2. So what we're going to do is the question is, what do I multiply 3x by to get to 6x cubed? And the answer is 2x squared. So I'm going to take that 2x squared and multiply both of these by it. So 6x cubed plus 4x squared. And I'm going to subtract them. So when I subtract them, these cancel. So I get 0x cubes. And right here, I got minus 5x squared minus 4x squared. This minus is from right there. It gets distributed. So you get minus 9x squared. And we'll just carry down the rest. Minus 3x plus 4. So now we're going to do the same thing. So what do I multiply 3x times to get minus 9x squared? Well, it's going to be minus 3x. So minus 3x times that, so minus 9x squared, minus 6x, and I'm going to be subtracting it. So again, this minus sign kind of distributes. So 9x squared plus 9x squared, these always cancel. Minus 3x plus 6x is going to be positive 3x. Carry down the 4. And then again, what do we multiply 3x plus 2 by to get to 3x plus 4? Well, it's just going to be a plus 1. 3x is already a 3x, so minus 3x plus 2. You're going to get just number 2. So for the answer, it wants the quotient, which is this part right here. This is our quotient. Plus our remainder divided by the divisor. This right here is our divisor. So what's going to be is divisor plus 2 over, that's our remainder, 3x plus 2 over our divisor. And this is the answer I wanted. Okay, going on to part B. It's going to be pretty much the same idea. I'm going to erase this, at least the bottom part. I'll leave the top part so you can see the answer still. Sorry, just one moment. That's about good enough, so I'll go ahead and stop in 1 second. Okay. So it's going to be 3x to the 4th plus 2x to the 3rd plus 4x squared plus x minus 5 divided by x squared plus 2. So the question is going to be, what do I multiply x squared by to get to 3x to the 4th? Well, that's going to be 3x squared. So I'm going to subtract 3x to the 4th. So what I'm subtracting is I'm multiplying 3x squared times this whole thing, right? So you get 3x to the 4th plus 6x squared. And I'm going to put it over here so I don't mistake it to be with this x to the 3rd. Because I can't add and subtract a 6x squared and x to the 3rd. When I subtract them, these first two get canceled. So I'll get 2x cubed. Didn't add or subtract anything. And then 4x squared minus 6x squared is going to be minus 2x squared plus x minus 5. Now, what do I multiply x squared by to get to 2x cubed? Well, that's going to be plus 2x. So we minus 2x times that. So 2x cubed plus, leave this one blank again, and then 4x right there. Go ahead and go ahead and add these down. These cancel. We get minus 2x squared minus 3x, because x minus 4x minus 5. Now, we get from x squared to negative 2x squared, it should be times minus 2. So minus negative 2x squared, and then minus 4. So what we're going to get when we do all this, we get minus 3x plus 9, or sorry, minus 3x. It's going to be minus 5 minus minus 4. So it's going to be minus 5 when we distribute these. Minus 5 plus 4, so it's going to be minus 1. So it's going to be 3x squared plus 2x minus 2 plus minus 3x minus 1 over x squared plus 2, because that's our remainder over our divisor, and that's our quotient out front. And that is the answer. Okay, I want to clear the workspace a little bit. Now we're going to do synthetic division to divide the following polynomials. Give the answer as the quotient plus the remainder by the divisor. So, how we do our synthetic division is I'm going to go ahead and put all my quotients, not quotients, all the numbers on my x squared and stuff. So, 1, 3, minus 1, 7, 2. Gotta be careful. If it if there was no x squared here and I could just skip this, in the x squared spot, we wouldn't just skip it, we'd put a 0 there. So just be careful. So, and then what are we going to be dividing it by, like synthetically? We're going to do 3. We get the 3 from right here. 3 minus 3 would make that 0, so we're going to divide it by that. Okay, so when we do it, we always bring down this first one. So the 1 always gets brought down. One time, and then what goes right here is that 1 times 3. So it's going to be 1 times 3 is 3. 3 plus 3 is 6. 6 times this 3 is going to be 18. Minus 1 is going to be 17. 17 times 3 is going to be 51. Plus that is going to be 58. Times 3 again is going to be 174. Plus 2 is going to be 176. And this last number we have here is always going to be a remainder. So, our answer is going to be, in order to get the quotient again, is, if we think about it from here, right? As we went to the left here every time, this was an x squared, x cubed, x to the fourth, where this one start off just a number. It's going to be the same idea here, right? So it's going to be, or in other words, this starts as an x to the fourth. We're going to drop down 1, so it's going to start as an x to the third. So 1x to the third plus 6x squared plus 17x plus 58. And then I want our plus the remainder divided by the divisor, so plus 176 over x minus 3. And that is the answer. Okay, continue on doing this again. This time our divisor for part B is going to be minus 2. Our coefficients are 2. You see how this is x to the fifth, and there's no x to the fourth or x to the third. So we're going to have to put zeros where we don't have one. So we don't have an x to the fourth. We don't have an x to the third. 1 for x squared, minus 5 for just the x, and 1. And whatever this is going to be the last one, that's going to be our remainder. So bring down the 2. 2 times minus 2 is minus 4. Add these together, you get minus 4 times negative 2 is going to be positive 8. Add those together, you just get positive 8. Positive 8 times negative 2 is going to be minus 16. You add these together, you get minus 15. Times negative 2 is going to be 30. You get positive 25. You get minus 50. And you get negative 49. So our answer is going to be, this started off as x to the fifth. So it's going to be 2x, 1 less than 5 is 4. Minus 4x cubed plus 8x squared minus 15x plus 25. And then plus our remainder, which is negative 49, over our divisor, which is x plus 2. And that is our answer here. Okay, so now doing number 55, use the remainder theorem to evaluate the polynomial f of x equals 3x to the fourth plus 2x squared minus 4x plus 1 at f of negative 2 show all work. So what the remainder theorem is talking about, and it's really cool, is that if you do synthetic division with negative 2 on that thing, on this whole, so it's going to be 3, there's no x cubed, so it's going to be 0, 2, minus 4, 1. Whatever we get right here, which is our remainder, is going to be the same thing as if we just plug negative 2 into this. And that's what the remainder theorem is saying. So let's go and do our synthetic. So bring down the 3. 3 times negative 2 is minus 6. Bring down that minus 6. Negative 2 times minus 6 is going to be positive 12, which is 4. That's 14. 14 times minus 2 is minus 28. You get negative 32. Multiply that times negative 2, you get 64. Add those together, you get 65. So what this is saying is this means f of minus 2 is equal to 65. And that's the final answer here. So now we're going to use our remainder theorem to determine if negative 5 or 2i are zeros of the following polynomial. So again, our remainder theorem is that if I do synthetic division with negative 5 on this, which is going to be 1, 6, 9, 24, 20, ... If this is a 0, then right here what we should get as our remainder should be 0. That's what that means. So I'm going to do synthetic division on this. If I get out 0 right here, then that means yes, it is a 0. If I don't, then no, it's not. So I'll bring down the 1. 1 times minus 5 is minus 5. 6 minus 5 is 1. 1 times minus 5 is minus 5. 9 minus 5 is 4. 4 times minus 5 is minus 20. Bring that down. That's going to be 4. 4 times minus 5 is minus 20 again, and that's 0. So what that means is minus 5, that's for sure 0. And now let's test if 2i is. Well, I could do this whole thing again. We're starting with 2i here, or since this first part worked, and this will only be true if the first part worked. And because if minus 5 did, I can just do it again on this reduced one and do 2i here. And this will be helpful because it'll make just life a little bit easier because I don't have to deal with as much. So I'll bring down the 1. 1 times 2i is 2i. 1 plus 2i is 1 plus 2i. 1 plus 2i times 2i is going to become 2i plus 4i squared, 2i minus 4. Over here, you can just do 2i times 1 plus 2i, same thing as 2i plus 4i squared. I squared is -1, so it's 2i minus 4. So when we add these together, we just get 2i. And lastly, 2i times 2i, we're going to get 4 times I squared, which is I squared is -1, so minus 4, 0. So they both were zeros. So 2i. If positive 2i is a 0, we also would know that minus 2i is a 0. But we only need to determine if these two are zeros. So I'd say are both zeros. And yes, that's basically the answer for there. So
hello, new voice here. Gonna wrap up the college algebra review part 5. We only have 4 more problems left, so I'm gonna start with 57. We want to use the factor theorem to determine if x plus 3 or x minus 3i are factors of the polynomial given. Factor theorem basically tells us that if we use synthetic division to divide x plus 3 or x minus 3i into this polynomial, the remainder is the value of the function f at -3 or 3i. And they're factors if the remainder is 0, right? Oops. Trying to move the... Okay. I'm going to get myself some space over here. So we're going to set up synthetic division. So basically for synthetic division, we're just going to write the coefficients of f on the top. In this little box, we're going to write the root of what we're dividing by, which in this case, we're going to start by divided by x plus 3. So that root is -3. Then our coefficients, let me erase this stuff over here. Coefficients are as follows. We have, so it's 1x cubed plus 4x squared plus 9x plus 36. We start by dropping the first one down, then we multiply through by our root, so we get -3, add to get 1, multiply to get -3, add to get 6, multiply -18, add to get 18. By factor theorem, this means that f of -3 is 18, which is not 0, meaning that x plus 3 is not a factor. Now we're going to do the same thing with -3i. If I can figure out how to move this. One sec. Okay. That's what I'll move. I think it's limited to the space I have. So we're just going to scroll down. And yeah. Okay. So now I'm going to go down here. And you might have to write along with us because right now I can't seem to figure out how to avoid erasing some of this work after we're done. So the root for the next one we want to check is, so it's x minus 3i. So the root is 3i, and we're going to do the same process. So it's 1, 4, 9, 36. Turn off the 1. 3i, we get 4 plus 3i. We multiply by 3i again, we get 12i. And then 3i times 3i is -9. So we do that addition, we just get 12i. Add those together, 3 times 12 is 36, I times I is -1, so we get -36. Our remainder is 0, so x plus 3i, or rather, x minus 3i is a factor. So that's how we do, that was 57. And I'll pause, or I'll ask you to pause the video and catch up with us in the writing, because I'm going to have to erase some of this to make space. Okay, well, I was having some slight technical issues there, trying to figure out how to make space. So hopefully we got all of that down, and if you need to rewind, of course, that's fine, rewind and pause. I'm going to move on to 58 and work in this space over here to my right. So we want to find all the zeros of the function 4x cubed minus 20x squared plus 33x minus 18, given that 2 is a 0. So we want to write, so what we're going to do is long division. Anytime we get something more than, we use synthetic division when we want to check divisibility. Basically, does this linear root or this linear factor divide into this polynomial? Because then you can just check if by factor theorem, if the remainder is 0 or not, then it would divide. But if you have anything larger than a linear factor and you want to check if it divides or anything else, you're going to have to use long division. And in this case, we're going to get a quadratic as an answer. So we're going to divide x minus 2 into 4x cubed minus 20x squared plus 33x minus 18. And that's going to give us the quadratic that's left over. And then once we have that quadratic, we can factor it and then write everything as in a linear form. Great. So I want x minus 2 to cancel with 4x cubed. So I write 4x squared over here, and I get 4x cubed minus 8x squared. Subtract. These cancel. I get negative 12x squared. So I get minus 12x. So I get minus 12x negative 12x squared plus 24x. Oh, wait, right. My bad. That was what was left over. Let me go and bring down the 33x as well, so we know where we're at. Okay, cool. And now when I bring this down, I get negative 12x squared plus 24x. Subtract again, these cancel like we designed them to. And then 33 minus 24 is 9. X minus 18. So now we do plus 9. And this is 9. Oh my gosh, just an ugly 9, sorry. 9x minus 18, because 9 times x minus 2 is 9x minus 18, 0. So it divides, which is fine. We already knew that. What we wanted was, oh, this thing is, okay, there we go. Give myself some space over here. What we want is this. This is what's left over. So we take one factor out and we look at what's left, because now we want to break this up into the other factors. So it's 4x squared minus 12x plus 9. We want to factor this. I'm trying, sorry for the pause. I'm trying to think if we can use anything more simple than quadratic formula, but I think that it doesn't look, yeah, anytime you have a leading coefficient that's not 1, it's going to be hard to factor directly. So it's probably easiest to just use quadratic formula. So we're going to get negative b, which is 12, plus or minus the square root of b squared, 144, minus 4ac, which is 4 times 4 times 9, which is 4 times 36, which is 120 plus 24. Oh, it's 144. Look at that. Maybe this is easier than I thought it was. Right. Okay, so that's 0. So we get one solution. It's all over 2 times a, which is 4. So we get 8. This is square root of 0, so it's 12 over 8. It's repeated, though. Because the discriminant, this thing, equals 0, it means we have a repeated root at 12 over 8. Which is, we can simplify, 3 over 2. And I rewrote x minus 3 halves as 2x minus 3. They have the same root, but this will FOIL correctly, whereas x minus 3 over 2 would not. So let's remind ourselves of the actual question, which was to write the function as linear factors, right? So f of x is x minus 2. It's 2x minus 3 squared. And this could also be yeah. You could also write this as x minus 3 over 2 squared. But yeah, that's how we do that problem. Long division, we get the quadratic. We solve that quadratic with the quadratic formula, and then we find those factors, and then we write it in this form. So that's factored form. Okay, only a few more questions. Okay, now that I got all of that cleaned up, we're going to look at 59. Write a polynomial p of x of degree 3 in standard form with zeros -5, root 2, and negative root 2. And we're supposed to show all work. So what we're going to start with is just writing the zeros as factors. So p of x is going to be, well, if it has a 0 of -5, it has to have a factor of x plus 5. And then same thing with plus and minus root 2. So that's p of x. And we would be done, except that it wants it in the standard form, which means that we need to distribute. I'm going to start with these two, because it's a difference of squares, and it'll get rid of my square root 2. So I don't have to worry about that moving forward. So this is x plus 5, x squared minus 2. Now I can finish with some FOILing. So it's x cubed plus 5x squared minus 2x minus 10. And that is my answer. That is p of x. And it is degree 3 because we have 3 roots. Great. Okay, so that's question 59. Now we want to do question 60. I think I have enough room to just scroll down. We want to find all the zeros of the polynomial f of x given here, given that -3 and 4i are zeros. So this can be a little daunting because it's quintic, that is, it has degree 5. But in this case, they actually give us a lot of useful information. So we know that x plus 3 divides because -3 is a root. 4i is a root, which means -4i has to be a root because this is a constant, or this is a polynomial with real constants. Just assume in this class that if you're given an imaginary root, then its conjugate, that is with a sign flip, also has to be a root. So 4i and minus 4i are zeros. So x minus 4i, x plus 4i do as well. Great, so we're going to basically combine the last 4 or 5 problems from this review into this problem. What we need to do is we need to take the fact that x plus 3, x minus 4i, and x plus 4i all divide to simplify the f to a quadratic. So we're going to do long division. Before we do that, we need to combine these factors into cubic. so that we can do long division in one step instead of having to do division 3 separate times. So I'm going to write that as, I'm going to call it G. This combination of factors I'm going to call G of x is x plus 3, x minus 4i, x plus 4i. And we're going to simplify that. X minus 4i, x plus 4i is the difference of squares. So this becomes x plus 3. X squared minus 16i squared, which becomes x squared plus 16, which is x cubed plus 3x squared plus 16x plus 48. And now we do long division. So, set it up the same way. We're dividing x cubed plus 3x squared plus 16x plus 48 into, what was the, scroll up a little bit. This iPad, man. Okay, so it's x to the 5th. Oh, the text is all jumbled together. It's x to the 5th plus 3x to the 4th. Get this one piece at a time. Plus 14x cubed plus 42x squared. 14x cubed. 42x squared. Minus 32x minus 96. And this might look pretty bad, but remember that we're dividing a cubic into it. I'm going to move that out of the way. Okay, great. So we want x cubed and x to the 5th to cancel, so we're going to write x squared, and we get x to the 5th plus 3x to the 4th plus 16x cubed plus 48x squared. And you can already see this is simplifying really quickly. So this is, these cancel, these cancel. This is negative 2x cubed minus 6x squared. So now we do minus 2. And we get negative 2x cubed minus 6x squared minus 32x minus 96, which is exactly what it needed to be, because these other terms drop down here, so they all cancel, and we get remainder of 0. So we know that x squared minus 2 does in fact divide. And because we know x squared minus 2 divides, oh, this is a mess, sorry. I hope this is, okay, move that out of the way. I was just double checking that the question wanted the zeros, right? So the zeros of f are as follows. That's a mess. Move that up, move that up, move that up, move that up. Awesome, okay. Zeros of f. So we were given 4i and negative 3. So we have negative 3, 4i. We deduced negative 4i as well. But then we also found that plus and minus root 2. I'll make a comment on that. So x squared minus 2 equals 0. X squared equals 2. X equals plus or minus root 2 is where those roots came from. So that's how you do this problem. You recognize they give you one complex root, you have the other conjugate, then you divide through. So you build g of x, which is this cubic containing all the roots we know it has. Then we do long division to find the roots we didn't know that it had immediately, which is x squared minus 2. What roots are those? Well, it's plus or minus root 2. And so we have 5 roots for a quintic polynomial. All right, now we're going to move on to the last 2 problems of the review. Okay, great. So we're moving on to the last two problems. This is problem 61. So we're going to find all of the zeros and the multiplicities of the function, beginning by finding the possible rational zeros, comparing the possible values with the graph of the function, a calculator. Check the value using division. Show our work. Okay. So all the zeros, right. So I've graphed this already, and I know that there are zeros at -5/2 and 1 with a possible bounce at 1. And a bounce in a graph just means that the multiplicity should be even. So now I want to check this with synthetic division. I'll do the 1 case and leave the -5/2 case as practice. So we'll just use synthetic division. We want to check 1 is a root. So we write down our coefficients. That's a disgusting 3 and 20. Okay. And as always, we drop the first one. We multiply by the root every time. We add 12, -20. Okay, so 1 is a root. Great. And so now what we want to do is we want to go through and do long division to find the quadratic that makes up the rest of the root. Oh, when I move it, it sometimes doesn't grab the rest of it. I'll just have to erase the rest. That's fine. So we've shown that 1 is a root, and we know that -3 is a root. And 1, we know, has to have even multiplicity. So it either has multiplicity 2 or multiplicity 4 based on the bounce. So we're going to divide through, and we're going to do a long division with x plus 5/2, which I'm actually going to rewrite as at 5x, or 2x, oh my gosh, 2x plus 5. I'm going to go and erase the rest of this. Nope. There we go. Okay, and we're going to multiply it by x minus 1 squared as an even multiplicity because it bounces. And we're going to guess that it has multiplicity 2 and do our long division. And if it has multiplicity 4, we'll end up with a quadratic with more roots of 1. So we're dividing this into our original, which was 2x to the 5th plus 3 plus 9x to the 4th. It's x to the 4th. I just realized I forgot to write this one over here. It's there in the addition. I just forgot to write it. Okay. Right. 2x to the 5th plus x to the 4th. X to the 4th plus 9x squared minus 32x plus 20. And then we're going to do, oh my gosh, we need to rewrite this in standard form, right? So these are the correct roots, but we want to write it in standard form. This is 2x plus 5, x squared minus 2x plus 1. This is 2x cubed minus 4x squared minus 10x. And then plus 2x plus 5x squared. So I'm doing this one at a time. So I did it with the 2x and I'm doing it with the 5. I already did the minus 10x plus 5. This is equal to 2x cubed plus x squared minus 8x plus 5. Okay, so now I'm going to take this up here. I'm going to rewrite this and then erase the rest of it. Okay. Excellent. So we have 2x cubed plus x squared minus 8x plus 5. We're going to erase our work from earlier. Great. Okay, now we can actually do the long division. Great. Okay, so it should be x squared, because we want to cancel 2x cubed and 2x to the 5th. This is 2x to the 5th plus x to the 4th minus 8x cubed plus 5x squared. These cancel, these cancel. We end up with 8x cubed plus 4x squared minus 32x plus 20. And now this is actually really convenient because we just need to add 4. And then we get 8x cubed plus 4x squared minus 8, or 32x plus 20. Everything cancels. So we know it divides, which is great. So it divides. And now, again, when I move, it keeps it with it. It's so annoying. Okay. Now we know that x squared plus 4 is the other one. So I'm going to have to erase all of this. So hopefully you have a chance to write that down. If you need to go back, you can. So now we just need to know what the factors of x squared plus 4 are. Okay. Okay. So x squared plus 4. So x squared is negative 4. If we set it equal to 0, so x is plus or minus 2i. Okay, great. So the roots. We knew that negative 5/2 was a root from the graph. 1 with with multiplicity 1. 1 with multiplicity 2. I'm putting multiplicity in parentheses. Hopefully that should be clear. And then 2i, that's not in parentheses. Oh my gosh. 2i with multiplicity 1, negative 2i with multiplicity 1. And the multiplicity should add up to be 5 because it's a quintic polynomial. Okay, great. So that's problem 621. I'm going to erase all of this. And then move down and do 62. I guess I could pause and erase. I might go back and do that. Maybe not. You can skip ahead. Okay. Oh my gosh. The iPad's lagging. Great. Okay. Now we're going to scroll down and do 60. Look at this. 62. Okay. We want to write a polynomial of degree 3 in standard form with integer coefficients in zeros, 3i and 4/5. There's two things that integer coefficients tells us. It tells us that our coefficients are real, so 3i needs to also have negative 3i as a root, and that 4/5 needs to be rewritten. So we're going to have factors x minus 3i, x plus 3i, and because 4 over 5 needs to be rewritten with integer coefficients, 5x minus 4. And now to get it in standard form, we just need to distribute. So I'm going to start with the imaginary terms. X minus 3i and x plus 3i becomes x squared plus 9 times 5x minus 4, which becomes 5x cubed minus 4x squared. Plus 45x minus 36. And that's our answer. All right, great. Good luck on y'all's exam. Hope it goes well. Hope this review is useful. Please leave a comment on the YouTube channel if you think we should change anything or if you notice any mistakes. And you can email us at, it should be osu.mlsc@gmail. All right, good luck.